Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's a real pleasure to welcome Olivier Chappell here today. Olivier is a senior researcher at Yahoo Research. Before that, he was at Max Planck in Tübingen, and he worked with Vladimir Vapnik on support vector machines. He's worked on semi-supervised learning, web search ranking, and he got his PhD in the University of Paris. And he's going to talk about new click models web search ranking today.
Thank you, Chris, for the introduction and the invitation. It's a pleasure to be here. What I'm going to talk today is some presentation I gave to www this year. It's a slightly extended version. So the talk is it's not so long. So feel free to interrupt me anytime if you have questions. What I'm going to talk today is about how to use clicks to improve web search ranking. And I will first review machine learning for ranking, even though I guess a lot of people are already familiar with that. I will still give a brief introduction. So here the goal is you have a query and a document, and you want to estimate the relevance of a document to the given query. And instead of using traditional information retrieval functions like BM25, now people use more and more often machine learning. So here I was just wanted to mention that here we are learning a relevance function, but in principle you could imagine learning a ranking. For instance, if you want to address the question of diversity. But it's a more complex, it's out of the scope of this talk, and here I'm just going to concentrate about learning relevance function. So to use machine learning, we need two things, features and data. So let me start with the data. So you typically have, for instance, judgments coming from human editors, which give some judgment on a graded relevance: perfect, excellent, good, fair, bad. And you could also have a pairwise preference judgment between two URLs. So this URL is preferred to that other one. So of course it's possible to convert the absolute judgment to pairwise judgment, but the contrary is not possible. So the reason why I mentioned pairwise data here, because we're going to use clicks as training data also, and in particular we were going to use clicks in the form of preference data. And something else we need also is feature vectors. So you have there could be 100,000 of such features, but they can be divided in three categories. The one which depend only on the query. For instance, it could be the type of query, the number of words in the query. The one which depends only on the document, like page rank or like the result of a spam classifier. But of course, the most interesting features are the one which depends on both the query and the document. Like for instance, I don't know how many words in the documents are in the query and so on. And now, once you have those, the training data and the features, so you just need to use some minimize some objective function. And again, those objective functions can be divided in three categories: pointwise, pairwise, and listwise. So pointwise is, for instance, a regression or classification, so where the loss depends only on a given document. Pairwise is where the loss is a sum over preference pairs, and listwise where the loss is defined over the entire list of documents associated with a query. So in this talk, I'm going to use pairwise loss, and in fact, I've been myself working on this kind of list-wise loss, and it turns out that the difference between all those kind of techniques is very small. So just like a pointwise algorithm, for instance, does already very well. So let me now talk about clicks. Why do we want to use clicks? The main reason is because we have like millions of users which give us valuable feedback about what is a relevant document, what is a non-relevant document, and so we want to leverage this relevance feedback. And yeah, so they are cheap. They don't cost anything, unlike the human editors that you need to pay, and you have magnetism more of these data than editorial labels. And so now, how to use clicks? So you could use it in two ways. I would say either as a target or as a feature. So as a feature, it's for instance, you're going to take the click-through rate of a URL and add it as a feature when you train your ranking function. And that's what, for instance, like Agishstein did in 2006. Or you can use it as a target, where now you're going to augment your training set based on the click information. So you're going to, in a way, you're going to use the clicks as a pseudo label. You're going to try to extract from clicks a pseudo labels, which is how relevant is that document for that query. So I think Thorsten Joachims was the first to talk about clicks as targets, where he was taking those preference pairs and he said those keep above pairs when you say if a document in position 2 is clicked and the document is in position 1 is not clicked, then the document in position 2 is more relevant than the one in position 1, and so you add these preference pairs to your objective function. So the main difficulty in using the clicks, and that's the motivation for this work, is the so-called presentation bias. The fact that you could have like a very relevant URL, but it's going to be shown in position number 9 or 10, and then people are not even going to see it and are not going to click on it. So if you just look at clicks, then you're going to think it's not relevant, but in fact the URL might still be very relevant. So the problem statement here would be what would have been the click-through rate of a given URL if I had shown it in first position. So that's what I'm going to try to address in this talk. I'm going to pretend that I'm going to observe like an URL in position 5, 6, 7, 8, and I'm going to try to predict what would have been this click-through rate if I had put it in position 1. So that's what I call like an unbiased relevance estimation, because then now you don't have a problem of position anymore. You normalize everything to position 1. And so I will review two types of click models. So one is a so-called position bias model, where we're gonna look at different positions, and for instance, if you say that you're going to say, in position 2, you're like 30%, there is 30% less chance than to be clicked than in position 1. So then if you observe a click-through rate of, I don't know, 0.3 in position 2, then it translates in 0.5 in position 1, something like that. And I will try to convince you that it's not a good type of model. And instead, the so-called cascade model, which was introduced last year by Nick Roswell and his colleagues from Microsoft Research Cambridge, is, I think, much more suitable for the task of click mining. So, but the model they proposed last year was somewhat limited on the kind of thing they could do. So that's why in this work we proposed an extension of their model. And after we were, and also something I want to say that we're going to do different compared to other click modeling work, is that the evaluation is going to be different, because we're not simply going to try to evaluate in terms of log likelihood of some session, some unseen session. Instead, we're really going to try to evaluate how good is this predicted click-through rate in position 1, because that's what we're interested in. Okay, so yeah, so position-based model. So the most naive thing you could think of is the simplest thing, which would be to look at the click-through rate in different positions, and you say, for instance, the click-through rate in position 1 is twice higher than the click-through rate in position 2. So I'm simply going to multiply all my, every time I have a URL in position 2, I'm going to multiply by 2 its click-through rate to try to unbias it. So that would be the simplest thing to do, but that's very wrong because the search engine has put more relevant documents in the top positions. So that would be correct to do if the search engine would output random documents, but hopefully that's it's not completely random. So you have so the problem is to distinguish the effect of the search engine putting more relevant documents in top position and the pure position effect of the fact that people are less likely to click in lower positions. So the second type of model, which is still a position-based model and try to distinguish those two effects, is the examination model, where you say a user is going to look at a certain position with a certain priority, BP, so which depends only on the position. And if he looks at this position, then after he's going to click on the URL with a certain probability, AU. So now the probability of a click is a product of two quantities, one depending only on the URL and the other one depending only on the position.
So that's integrated over queries?
Right. So in fact, so all what I'm going to talk about in this talk is for a given query. So everything is conditioned on a query. So yeah, I mean, I should write here like there should be a subscript Q and U, but I drop this Q everywhere. So now you estimate those parameters by maximum likelihood, and the reason, in fact, that now you can have a meaningful result is because of the variations in the search engines. So you're gonna be able to learn, for instance, from a given URL was shown in position 2 and then it was shown in position 4, and so you can compare for the same URL the click-through rate in position 2 versus the click-through rate in position 4, and now you can look at, in a way, intuitively, you look at this ratio and say that, when you go from position 4 to position 2, what is the difference in click-through rate? So that's a better model than the naive model. And a variation of this examination model is a logistic model, where now the probability of click is also depending on two quantities, one on the URL and the other one on the position, but the functional form is a bit different, and the good thing is that it's it's jointly convex in A and B, and so you can optimize it much more easily. So if you want to use a position-based model, I would say that you should use this logistic model, but now I'm going to try to convince you that you should not use a position-based model. Yeah, okay. Before that, I was showing you. I would like to show you this graph, which is so the effect on the position, the effect of the position on the click-through rate. The blue line is this naive method I was telling you about, which is, for instance, here, let's say in position 2, I have like 0.3, meaning that in average, the click-through rate in position 2 is 0.3 times the click-through rate in position 1. And this red line here is the priority, this BP here. So like a proper position-based model, what is the influence of the position? What is the influence of the position on the clicks? And you see that it decays much more slowly, and it makes sense because now you have decoupled the problem of the fact that the search engine puts more relevant documents in higher positions. Okay. So so here's an example of why a position-based model is not good. So we looked at some query logs. It was in the UK, and the query was MySpace, and the URL of interest was www.myspace.com. And so, because of the variations in the engine, sometimes the uk.myspace.com was shown in first position, and sometimes www.myspace.com was shown in first position. And so you can see that when www.myspace.com is shown in first position, it has a very high click-through rate, which makes a lot of sense, right? 97%. But then when it's shown after uk.myspace.com, it has a very low click-through rate, which makes sense again, because then it's just that everyone clicks on uk.myspace.com, so you have a very low click-through rate in second position. But then a position-based model will never be able to explain the fact that by going from position 1 to position 2, the click-through rate is almost divided by 9. So no position model can explain that. And I will argue that, in fact, if you work on click modeling, you should always keep this example in mind, because any click model you think of should be able to explain this situation, right? And yeah.
Has anyone done any work on looking at different kinds of queries? Like for navigational queries, like doing this might make, I can understand this in some way. Maybe for informational queries, you won't get this sort of behavior.
So, yeah, if you look, for instance, at this plot, and now you do it differently for navigational queries and informational queries, you would have like very different plots. In particular for navigational queries,
Should be conditioned on the
right.
type of the query.
It's gonna drop much more quickly for navigational queries. But I would prefer, in fact, that a click model in which I don't have to do to condition on the type of queries, that works for any type of queries. And the cascade model I'm going to talk about, in fact, works for any type of queries. And you don't have to do this distinction between navigational and informational. So the cascade model, as introduced by Nick Roswell and his colleagues, works as follows. You suppose that the user is going to look in position 1, and with a certain probability, he's going to click on the first URL. If he clicks, then he's satisfied and he stops his search. If he doesn't click, he goes to the next position, position 2, and with a certain probability, he's going to click on this second result. And same thing happens again. If he doesn't click, then he goes to the third position, and so on. So it's a very simple and intuitive user model. Just to be so now you have a probability for each. You have a probability for each URL of clicking. So then now I can write the probability of a click in third position by, for instance, this product here. So this is the probability that he doesn't click on the first one, the probability that he doesn't click on the second one, and finally the probability that he clicks on the third one.
This probability only depends on the position, no UI and the AE.
No,
this one.
The probability depends on the URL. URL only.
Oh, UI only.
Right. So here the notation is U1 is a URL shown in position 1.
Okay.
And so AU1 is the attractivity of the URL in position 1.
UI in position.
Right. So it depends only on the URL, not on the position. So some limitation of that model are obvious. So the fact that you will have, by definition, exactly one click by session. So because the user will always go to the next position until he finds something that he likes and he clicks on. So he can never abandon the search. And there cannot be multiple clicks because once he clicks on something, then he's done, and he's satisfied, and so he wouldn't click on the second position. So you could think that it's a very limited model, but just a simple model is already better than the position-based model.
How does it compute the AUs? How does it compute them?
So by maximum likelihood. Right. In fact, it turns out to be like a simple counting.
So it's just relative frequency, sort of.
But you cannot enumerate all those possible ordering, right? I mean, you can only compute this maximum likelihood using one particular ordering you have observed in your ranking.
That's right. So I take the the given session I observe in the click logs, and I can compute the probability of that.
But to get a true probability, you have to average across all possible different ordering, right?
No, but I don't want to. I mean, I'm not interested in that. I'm just interested. For me, I'm interested to evaluate by maximum likelihood those numbers.
So this number is.
It's observed random one for the one particular sort of ordering.
It's not order, right?
No. Again, this number depends only on the URL, not on the position.
But when you're computing that, right, I mean, AU1 is the first one and AU2 is the second one, right? But this ordering, I'm saying AU1 is first, AU2 is second, and AU3 is third. You only observe once. You don't observe, AU2 is the first, AU1 is the second, and AU3 is the third.
So, hold on, just to be, if I would swap the two URLs, imagine I observe first session and then I observe the same session in which the two URLs at the top are swapped.
Yeah.
And then I get a click also in the third position, then I will get exactly the same probability, right? Because I would just swap those two numbers.
That's right, you have to swap them. But the thing is, you don't have the observation for that. You can swap them in your computation, but you don't observe that. I mean, you only observe AU1 is the first, AU2 the second, AU3 the third.
But that's fine. I mean, Again, I'm going to I can compute the log likelihood of that session,
right?
Right? And I'm going to now find all those AU by maximum likelihood.
Yeah.
But in order to compute this, you have to see them in different orders. If you always see them in the same order, you'll not be able to compute them.
No, I will. Why not? So, by the way, it's this other one, the examination model. If I always see the same URL at the same position, then somehow it will be underdetermined. I mean, I will have like an infinite number of solutions, and I will not be able to extract any information. So for the examination model, I need to see the same URLs at different positions. But for this one, I don't think I need to see the same URLs in different positions.
The index, the U1, U2, U3 is indexed in URL, not position.
Not
That's right.
position.
But this particular product is computed in the order of AU1, AU2, AU3. This product is computed in that particular order.
All right.
Yeah. I mean, AU1 is independent of position, but this product has to be computed in that order.
Right.
Yeah.
But so
I mean, we can
it's
talk
not
about
an issue,
that.
right?
There may be some issues using that to estimate AU1. I think eventually you want to use this product as a way of estimating AU1, AU2, AU3, which is position independent.
Right. In fact, that will be when I said at the beginning, my goal is to estimate what is the probability of click in first position. In the case of the cascade model, that will exactly be this number, because if you put that URL in first position, then by definition the user always examines the URL in position 1, and then he's going to click with a certain probability, and that will be exactly that probability. So this AU is the same thing as a click-through rate in position 1.
Yeah. So yeah, I understand. Yeah.
All right.
Yeah. When you say it outperforms, do you mean it fits the data better, or it's more predictive of data that it hasn't seen?
In fact, I will come to that in the evaluation section.
I can wait if you're going to come.
Yeah, maybe that will be the simplest way. Yeah, the prediction of the AU are better. That's what I meant. So So in the work we have been doing, we do two extensions. One is to allow the user to abandon the search, and the other one is to allow the user to, to click on something. He looks at the document, is not satisfied by it. He comes back to the search result, and he clicks on something else. So with that, we have the possibility to have 0 or more than 1 click per session. So how to do this modeling? It's we use a Dynamic Bayesian Network, which is just almost the same thing as an HMM. So where here we have like hidden states, which are whether the user examined the URL in position I or not. So it's binary variables, whether the user examined the position I. We have an observed variable, whether there was a click or not in position I. Another hidden binary variable, what the user attracted by this URL, and what the user satisfied by this URL after he clicked. So all those hidden variables are defined at the session level, and then I have some latent variables here which are defined. You can think of those variables as like an aggregated version of those binary variables. Now, what are the equations defining this model? The same. It's as the previous model, this one. So you always examine position 1. If you don't examine a given position, it means you're done with your search, like in the cascade model, right? You're not going to examine the next one. Like in the examination model, you say that you have a click if only if you examine and you're attracted, and then you're attracted with a certain probability which depends only on the URL. Now, what is new are those equations. So now you're going to be satisfied with a certain probability, which depends on the URL. So, for instance, if you should think if this URL is spam, this SU is going to be very low. If you don't click, you're not satisfied, and if you're satisfied, you stop searching. And now, even though you were not satisfied, there is a probability 1 minus gamma that you're going to abandon your search, and with probability gamma, you're going to keep searching. Yes. All right. So it's a lot of variables. I hope you're not too confused.
I have a question. Do you have numbers on how often people are satisfied just by the snippets? So do we have some measure of that? Because that's going to be a problem with this.
Yeah, that's a very good point. So I don't have I don't have a number, but that's right. That it's a problem with this model because of this equation, right? You say if you are not click, you're not satisfied. Whereas the user could have found the information without clicking. I think it's quite small, but you should maybe do another extension of this model to try to include this case.
It's realistic to have gamma independent of I? Because I would think that as you examine results and you don't like them, so that gamma would actually decrease, right?
Right. You could have indeed some gamma which depends on the position. I think I've tried that and that didn't make a big difference. So you have to keep in mind also that, but then as a user keeps examining and he doesn't find something, the probability that he's going to keep examining is lower and lower, right? Because you would multiply like all those, gamma together, right? So you have kind of a natural exponential decay of not examining position I.
Question.
Yeah.
So if they click on some I, do you assume that the user examined every I before that?
Right. So so in this, it's the same as in the cascade model. You're gonna examine everything from top to bottom, and so there is no kind of skip, right? You don't start in position 1, then go in position 5. So it's really from top to bottom.
Is that realistic?
No. No. So no, there are two answers to this question. It's not realistic, but on the other hand, even though the model is very, a simplified version of what happens in reality, it's enough to capture a good, relevant information from the click logs. I think. And so finally, the quantity that so there are two latent variables of interest, right? This AU measure the perceived relevance, which is what is the probability that the user is going to click, given that he examined this URL, and then the other latent variable of interest is this SU that you can think of it as a ratio between perceived relevance and actual relevance, because it depends on what the user did after clicking on the page. And the quantity of interest is in fact the product of the two, because I'm interested in what is the probability that the user is going to be satisfied given that he has examined this position. And you can see, you can write it down easily, and you'll see that this product of this AU times SU. All right. So now, how do you do inference in this model? So it's the same type of thing as in a standard HMM. So we have used the EM algorithm to do that. So it's it's quite simple. So the E step is compute the posterior probability of all the indent variables given the value of AU, SU, and gamma, and that you do that using a forward-backward algorithm. And then the M step is given all those posterior probability, update your model parameters AU, SU, and gamma. So the good thing is that you do that independently for each query, and so there is no big coupling over like all queries, and so that can be efficiently done. So I think, in our implementation we have we can process around 10,000 sessions per second, and so in the end, it takes just several hours on a MapReduce cluster to process a couple of months of click data. So so it's just to say that it's not the computational time is not an issue. We have also done two extensions where we have introduced two virtual positions. One is a position 0 and the other one is position 11. So the position 0 is meant to capture everything which happens before the first document. So for instance, if the user clicks on some query reformulation or query suggestion, and the position 11, if he clicks on something below the last position, like click on the next button. Yeah.
So what happens if a new URL, you have to have seen the URL to know what AU is for,
right?
So fresh new URLs like news or something, you just don't handle them.
I don't know anything about that. Yeah.
So if you run this you'd have to run this on the index all the time to just keep it up to date if you use this for
Well, but the thing is that after I'm going to use those quantities just to extend my training data, right? So I'm going to learn a ranking function after based on those AU and SU, right? So just think of them as additional editorial judgments, right? So I'm not going to use that to do the real ranking, right? I'm still going to rely on a ranking function which takes a set of features and input and so on.
Could you just try going the other way, where you would parameterize AU and so on and SU based on a bunch of features, and then just learn the parameters of the discriminator model, for example, instead?
Right, and I think that would probably be the right thing to do. Now it's just more challenging to do because you have to, in the same time, you have to take care of the click logs and all the features for all the URLs. And so, the learning of the ranking function and the click mining is interleaved, right? And so so again, I think it's the right thing to do, but that seems very challenging to do. Okay, so experiments here. So first let me some definitions. I was speaking of session, but I didn't really define what is a session. So here, a session for me is simply like a query issued by a user and the set of URLs he clicked on. So that doesn't include any query reformulation or anything. We only consider the first page of results. And all the cases where the user, click in position, let's say position 7, and then clicks in position 5, those sessions, in fact, have zero likelihood under our model. So we decided to throw them away. Another possibility would be to, pretend that the one in position 5 was before the one in position 7, but we just threw them away.
What fraction of sessions are like that?
So it's about, I don't remember, I think it's 3%. But in terms of number of clicks, it's higher because, the more clicks you have, the more likely it is that you have those kind of reverse ordering of the clicks. So and here those experiments are going to be on 1 month of UK logs. So now let me come to the experimental validation, and I think it's important for anyone doing some things on click log mining. So I've seen a lot of papers which simply look at the likelihood of the click models on unseen sessions. And even though this kind of measure is interesting, it doesn't really tell you how good is your model in terms of predicting the relevance of a URL, right? What you're interested is, what is the value of AU? Is it a good prediction? So I think your evaluation should really try to address this question. And the reason why I'm pointing that out, because I have another colleague at Yahoo, Georges Dupré, who has also done some works on models for click logs. And in fact, if you compare different click log models based on either the likelihood on unseen session or these settings that I'm going to describe, you would see completely different conclusions. So it's so the setting in which you do is important. So again, how to evaluate how good is how good a prediction of AU. So AU here, it's you can think of it as the probability of click in position 1. So to see if you've done a good job in prediction, a natural thing to do is, for a given query, you're going to look at the URLs which both appeared in position 1 and some other position. You're going to hold out all the sessions in which it appeared in position 1 as a test set. You're going to use your click models to predict the CTR in position 1 based on all those other sessions in which the URL appeared from position 2 to 10. And now, once you have this predicted CTR in position 1, you can compare it to the real click-through rate in position 1, those held-out sessions, and you can have a measure of difference between the predicted click-through rate and the actual click-through rate. Yes.
But your model can actually predict the click-through rate at any position, right?
That's right.
So basically, in essence, you can actually, compute just like any other, position-based model. You can compare your model with position-based model on the click-through rate, because your model is actually can do both, right?
Right. So instead of having as a test criterion the predicted click-through rate in position 1, I could have like the predicted click-through rate in position 5, let's say, right?
Yeah.
And do the same thing.
And you can actually compute the log loss of actual clicked position, right? Because you know the session, you know which one has been clicked, what are the URLs above, and using your model can exactly compute on that position what the click-through rate is, given the previous URLs.
Right.
And you can actually compute the log loss.
Yeah, but again, the log loss, what is important is that if I'm going to use as a criterion, let's say the click-through rate in position 5, I don't want to have in any of my training data a click in position, any observation in position 5.
Yeah, I understand your motivation, but I think it's just for comparison based, right? If somebody has a position-based model, you can also have a position-based model and compare apple to apple.
Yeah. Well, no, I mean, I can compare position-based model. In fact, I'm going to compare position-based model here because all those models can predict something in position 1, right?
Okay. And all other positions. Your model can also predict.
Yeah, but for simplicity, we might as well just do position 1, right?
I just wondering, if you have other positions as well.
So here are the results. Sorry, yeah.
Question on the previous slide. Does this cause sort of a bias because you're only looking at queries where the first URL isn't always the same?
That's right.
So
yeah.
sort of queries that aren't necessarily quite as navigational.
So I think ideally what you would like to do is to to introduce some random noise in the search engine to control for that.
But assuming you can't do that, then
yeah.
Okay.
I think it introduces a bias, but I still believe that it's kind of more reasonable way of evaluating than again the log likelihood on unseen sessions. Yeah.
That question. So how often do you see that these positions, I mean the URLs switch positions, or because I would expect that you retrain the engine and now suddenly you change the position and you have another URL on that position from now on. Right, so up to some point you have one URL on the top position, and then after that point you have this other URL on the top position, and that one goes down the position, but it's not like it's random switching between.
No, it's kind of random. I mean, it's just, I mean, I don't know. When I observe the click logs, right, it turns out that, because of like some nodes going down or whatever reasons, right, the ranking function is always changing. So, I would observe that, sometimes, I mean, that's what this example I gave at the beginning with like myspace.com, right? Sometimes it's like uk.myspace.com in first position, sometimes it's www.myspace.com in first position.
But theoretically, right, if the nodes don't go down, then, and there are no new URLs that are more relevant than this.
Right, that should be constant.
That should never change, right? So.
Yeah. So then in that case, if the ranking was always constant, I couldn't use this thing for evaluation. That's right. So the y-axis here is the mean square error between the predicted CTR and the actual CTR in position 1. And the x-axis is the minimum number of sessions I've used for training. So on the right-hand side, you could think it's more like all the queries for which I had a lot of data, so more navigational queries and URLs. And on the left-hand side is just everything. So the two models which perform best are the cascade model and so this DBN extension. And interestingly, you can see that all the position-based model, which are examination, so CoEC here is this naive model that I talked about at the beginning. And the green one is a logistics. So all of them go up on the right-hand side. And it's in fact because of this reason I gave at the beginning, this MySpace, this problem with myspace.com query. In fact, it's more in the right-hand side. You have like only this type of queries, and for this type of queries, the position-based models do very bad, and that's why it goes up. Whereas it should go down, right? Because the more training data you have, the more accurate your model should be. So when I said earlier that the cascade model was doing better than position-based model, in fact, that's you can see it from this graph, for instance. Okay, and here the mean square error is a function of gamma. So gamma is the probability of continuing the search if you're not satisfied. And you can see that there is a minimum at 0.9, which means that users are like quite persistent because they're going to keep searching with 90% chance. But the putting gamma equal 1 is in fact almost as good, and I will come back to that at the end of the talk.
I thought you were learning gamma?
Yes. I've done two versions. One in which I fix gamma, and the other one in which I learn gamma. Yeah. But there was a question? Oh, okay. So here I'm going to present some results on which I simply sort the URLs according to their predicted score. So there is no learning. We'll come back to that later. But so I compute the NDCG for different click models, and so I think I kept all the URLs for which I had at least 10 sessions, and all the queries for which I had at least 10 URLs. And so the DBN model does better than the position-based model, the logistic model and cascade model. And the difference with the 10 nodes, the 12 node is the one where I have those two virtual nodes at the top and the bottom, so that helps a bit. And also the satisfaction. So here I rank according to the product of attractivity times satisfaction, and if I rank only according to the product of only according to attractivity, it's a bit worse. And now I can compare that to a real function that I'm going to learn using plenty of features and editorial data, and that would be about 4% better. But which is, it's just to give you an idea of the difference. So of course, you cannot really compare because this, the machine learn ranking function uses more information. It uses features and it uses editorial judgments, whereas like the clicks don't use any of those things.
So it was trained with NDCG or DCG in mind, whereas this were just clicks.
Right.
So a different evaluation, different costs.
Yeah. So this one is heavily biased towards editorial judgments, right? So what we've tried is to include this product AU times ASU as a features in the ranking function, and you can get almost 1% improvement in the ranking function. Yes.
NDCG for this particular query is similar to the NDCG for random queries, or is this very different? Because you chose queries with some specific properties.
Right.
You have the randomness of showing the URLs in different orders.
Oh, no. So that one is not the case. So that's a different evaluation here. So for that evaluation, I'm gonna look at all. I'm going to look at all query URLs which appear in my click logs. So that was only for the previous evaluation where I was doing this. I was trying to see how the click model was predicting the click-through rate in position 1. So for that, I had like a kind of very kind of specific setting. But for that experiment, I'm using all sessions, all queries.
You need to have a certain number of URLs, views of the URL, right, to be able to estimate the parameters.
That's right. So it's at least 10 sessions here.
It's included in 10 sessions. So.
Right.
But again, so this only applies to the AUs you've learned, right? So new URLs, you won't be able to compute a feature.
Yeah.
So you just some default value in that case.
No. I'm not going to use that in practice, right? It's just to see I was.
The set that you have to see the values.
The main point of this experiment was to compare different click models and to see if you would take the attractivities coming from different click models, like how well they would, how well they would rank the URLs. But I'm not going to use that in practice. Well, in practice, what I can do is to use it as a feature.
But that's what I'm saying.
But as a feature, if it's a new URL that I've never seen, then it's just going to be like some default value, right?
Okay. So it has to be robust to use that default value.
Yeah. Instead of using it as a feature now, I can use it as a target. So when I say as a target, it just means that I'm going to, augment my training data, and I'm going to build preference pairs. So I'm going to have one set of preference pairs coming from editorial labels, and one set of preference pairs coming from the clicks. So the one coming from the clicks are going to be, whenever you have a URL for which AU times ASU is bigger than for some other URL, I'm going to say I have a preference pair. And now I have an objective function to optimize, which is of this form, where I have a loss function here, which penalizes whenever the preferred URL has a smaller score than the non-preferred URL. So, for instance, you could take like the the square hinge loss. And so there is two quantities. So this one depends on the editorial data, and this one depends on the click. And now you have like a factor delta here to do the balance between the two. So if you put delta equals 0, you do training only on editorial data. If you put delta equal 1, you do training only on click data. And the best is, of course, to do something in between. So here it's like the relative NDCG relative with respect to only training with editorial data as a function of delta. So in the best value, you get about 2% improvement. And if you train only with clicks, you have like a 4% drop, which is consistent, in fact, with the 4% that I talked about before.
So the best is what? 80% editorial and 20% click?
Right.
Okay.
Well, I mean, 80%, 20% is kind of relative. I mean, because it depends on how you normalize things, right?
Well, what's the quantity of the editorial data and the click data?
You know what? I don't. There was more click data than editorial data. That's what I remember, but I don't.
Just guess some sense.
I would say maybe like 5 times larger. Something like that. I don't remember the exact number.
In terms of queries or in terms of pairs?
In terms of query URLs.
Query URL?
Pairs.
Query URLs pairs. Not in terms of preference pairs, in terms of number of query URLs. No, I mean number of XI.
I see. So are the depths different? The URLs you extracted from the editorial?
Yeah, so the depth is a bit higher for editorial, because for the clicks, you don't have so much depth.
Yeah. Okay.
You have less depth typically with the clicks. Yeah. Okay. Yeah. Well, we are running out of time. Sorry. So yeah, I just wanted to mention something important. In fact, if you have one thing to remember from this talk, it will be this slide. So it's I had a slide where I said optimal gamma was equal to 0.9. But in fact, if you take gamma equal 1, you have the estimation is simplified. And it's much simpler, and you can estimate AU and SU just by counting. And it's very simple, because you would, for instance, for AU, you would simply say, it's like a CTR. Well, how many times this URL was clicked? But instead of having number of impressions in the denominators, you would have number of views. Where now a view is defined by whether a click in a whether a click below or at this position. So if the user click in position 2, 7, and 3, you would say everything from position 1 to 7 was viewed, and position 8, 9, and 10 were not viewed. And that's like, incredibly simple, and that's so efficient to get rid of the position bias. Yeah, if anyone doing work with click mining, don't ever compute a CTR anymore. Just compute that. It works incredibly well. Yeah, never use standard CTR. Keep that in mind. So I'm going to finish quickly by some analysis on the discrepancies between editorial judgments and clicks. So as I said, we computed preference pairs from clicks and from editorial judgments, and we looked at cases where the preference was there was a discrepancy in the preference. And we asked judges, in fact, to give us a reason why there is such a difference. And we gave them 6 categories. So they could either say, well, there was any errors in the editorial judgment. Or the second category was the editorial judgment was correct, but maybe there was a problem in the editorial guidelines. So maybe we need to change the editorial guidelines. The third reason was something which will become more clear when I will show you examples, but basically it's some kind of like intrinsic contradiction between clicks and editorial judgments. The fourth reason is so the problem with click is the fact that they measure the relevance of the snippet, whereas the editorial judgment measures the relevance of the landing page. So we try to address that partially with these satisfaction variables, but it doesn't capture everything. And of course, you could be one reason could be click model is not accurate. So
Sorry. When you say the disagreement between preferences based on clicks, you mean the preference that as computed as your satisfaction rate?
Right, attractivity times satisfaction,
yeah.
Yeah.
The same? Okay.
Yeah.
Thanks.
Did you present these options to judges in different orders, randomly picked?
In fact, it was in this order, and so that's why it's true that when you would always often find a reason from 1 to 4. So those numbers are biased. So errors in editorial judgments. Okay, I mean they're not so interesting. We have noise. It's not. It will always be the case. The second category, I cannot talk much about it because I would have to tell you the guidelines. But the third and fourth reason, I'm going to give you some examples. So in all those examples, the query is in green. The first URL is the URL preferred by the clicks, and the second URL is the one preferred by the editors. So you can see, for instance, the query Adobe. People want to have the Acrobat Reader download and are not interested in the home page. HSBC, the bank, they want to go to the login page, internet banking. So, by the way, so this is an example of this third category. And for me, I find this third category very difficult because it's, maybe I don't know, is there a truth in there? Like, what should you put in first position? I mean, it's almost like a political decision to know what you should put in first position. I mean, personally, in fact, I would always follow what the users say, but I don't know, some other people would disagree. Paris Hilton, people want images, they don't care about their life. Rush Hour, they want the IMDb title and not the official home page. Perceived relevance versus actual relevance. You have, so of course spam pages, right? So the snippet looks very attractive, but it's the landing page is bad. So I'm not going to give an example of that. But there is also the quality of the URL abstract. So if the URL is very long, for instance, people think it's not such a good URL. So shorter URLs tends to be preferred. So that was done in the UK again. So far, it's funny to see that people prefer actually the .com extension compared to the .co.uk. Maybe they think it's more, I don't know, trustworthy. I'm not sure. Yeah, and you have also this domain trust. People are more likely to click on things they know. For instance, cricket score, they go to the BBC website and they don't go to the crickinfo.com, which is maybe...
Is this only in the UK?
Yeah, all that is in the UK. Hotmail, they go to the hotmail.com, not to this one. I don't know. What is this new hotmail.co.uk? And travel insurance, so I think this directline.com is a big company that people go to, even though they propose all kind of insurance, and they don't. But this travelinsurance.com is in fact specialized in travel insurance, but they still don't click often on it. Okay, so so as a conclusion, I hope to have convinced you that position-based models are not good for click modeling. So here we've presented some extension where the user can abandon the search, and also there is this satisfaction, which I think is important, which models the relevance of the landing page. And and the simplified version again, where you just do counting and you don't have to do any EM to estimate, I think is very simple and powerful.
By the way, the results you report are not based on the simplified version.
Yeah, that's right. They were based on the full version.
Do you have any comparison? Simplified versus
no, the only comparison I have is this one right here. So you could see, it's like 0.038 versus 0.04. So yeah, so in practice, in fact, you can, we first did this like DBN, and after we realized that the simplified version works so well, so we still use the DBN. But if you wanted to, if you wanted to try it, you might as well just use the simplified version, right? Yeah, and there is more generally a problem of evaluation, because all this evaluation was done using editorial judgments, and as I showed, there is like this kind of interesting discrepancies between editorial judgment and clicks, so it's not clear how you should evaluate. Okay. So that's it. So in fact, it was a talk I gave to Dub, and so I had like a last slide, which was the common points and differences with the talk just after me. I think so. It's a colleague from here. I don't know if some of you are in the audience, which was like. They have done something like very similar to our work. They also extended the cascade model to allow for users to abandon and to allow for the users to do multiple clicks. But so yeah, it's interesting to see that it was very similar. The only difference is this: we have also, in addition, this notion of satisfaction. We do exact inference, and also this evaluation again it was different. We didn't look at the log likelihood of instantiation, but we tried to really see how good is the predicted click-through rate in position 1. That's it. Thank you.
I have one questions from the top.
I have one question about. Any thoughts how this model would change for 2D presentation layout for image search, for example?
So, yeah, if you could have like a good user model of like how people would look at the images, then you could follow the same type of reasoning. So here the cascade model, again it's a simplified model. People go from top to bottom, and even though it's not really realistic, it's kind of enough to extract relevant information from clicks. So if you could have like a simplified model on how people look at image results, I don't know if they zigzag or I don't know exactly what they would do, but if you would have a simplified model, then you could do the same thing and have also a cascade model depending on how they browse the results. Yeah.
Thank you one more time.